Hello, and welcome to part 4 of the Assembly Language Sound series. When we last left our Assembly Language Sound code, we had a sine wave that sounded like this. Today, we're going to talk about why it sounds like that, and we're going to fix it. There's a lot to cover today, so we won't have time for chords like I thought we would, but they are coming soon. Today I'm also going to talk about a bug that had me scratching my head for quite a while. It is the mystery of the phantom time-traveling square wave from the future. Ooh. As a reminder, the way that code works is it has this thing called an oscillator. So this is a number that keeps on going up and up and up and up and up and up until it overflows, until it cycles back to 0. And every time it cycles back to 0, we will increment this number. So this is our index into the wavetable. So this is kind of like a fractional piece of a byte of the wave that we're going to play. So each time this goes up and up and up, we're still playing that same byte. But once this goes up past 65,1135 back to 0, then we move on to the next byte in our wavetable. And this is what that wavetable looks like for the sine wave. So it starts here, so we're going to play this for a bunch of times, and then once it overflows, we go up to here, then we go up to here, and then we do that for 8 bytes, and that's a full cycle. And then once we're done, we move down here and we begin the next cycle. And to illustrate, we can watch this in action in the debugger. Our oscillator starts here at 0, and each time through the interrupt handler, it goes up by a certain amount. In fact, it specifically goes up by this amount because that's the frequency of the note that we're playing. So a larger frequency will get us all the way around to 0 faster and will allow us to move on to the next byte of the waveform faster. So we're about to flip over. So once this flips over, here is our index. Here is our address of the next byte we're going to pluck out of that sine wave. So once this goes to 0, boom, we're now looking at the next byte. And then, of course, we stay here for a while until we go all the way up to... And this goes from 01 to 02. And that's what the oscillator does. So again, the oscillator is a fraction of a single byte. And the idea is that the waveform is so small, we're not going to be playing new bytes each time through our interrupt handler because the interrupt handler gets called so often. So this kind of tells us when it's time to move on to the next byte. So that's our review. So that brings us to the question, why does this sound like the CoCo has phlegm in its throat when it's trying to sing? This is an actual plot of those byte values of a single cycle of the sine wave. And it looks pretty good. It looks like a sine wave. But the problem is this isn't really what we're sending to the DAC. Because when we're sitting on this byte and the interrupt handler gets called over and over and over and over and over and over again, we keep on sending that same byte until it's time to move on to the next byte in the wave. So it actually looks more like this. We repeatedly send this byte, we repeatedly send this byte, and so on. And now this is looking less like a sine wave and more like a I don't know what that is. So the grungy sound that you're hearing is this. So the problem is we just don't have very good fidelity. We're hanging out on this byte for too long, and then we're jumping up to this byte and hanging out for too long, and then jumping up. We've got 256 bytes to play with in this page of memory. Why not make a 256 byte long sine wave? It would look like this. Now a full cycle goes from the beginning of this 256 byte block all the way to the end. And now we would be able to scan through this waveform much quicker rather than hanging out on a byte for a really long time. We might even be skipping over bytes because we need to get through this cycle fast enough to match the pitch of whatever note we're trying to play. So now rather than our waveform looking like this, it looks like this. This is way closer to a sine wave. Now you can see we still have this effect where we have like the same byte for a while. This is just round off error. These bytes are actually repeated in the waveform because we're rounding the double value of the sine function into integer values for the wave. But taken as a whole, this looks a lot smoother, and this should sound a lot better. In order for the code to work properly with a 256 byte long waveform though, we need to make some adjustments. Before continuing, a huge thanks to Simon Jonassen again. As you may recall from part 3, I talked about Simon Jonassen's work with music players, in particular his dipole player, which was the basis of all of the good ideas from that last video. And so now we're moving past that to his 4-voice music player, which was originally written for the CoCo 3. And yet again, I'm pretty much taking all of the ideas and a lot of the code straight from that player into what we're building right now. So huge thanks to Simon for sending this along to me and also for chatting with me and giving me some good guidance. And also to the other folks who worked on this. So Paul Fiscarelli also did a lot of the coding. And in turn, all of this was based on a lot of past work done by a lot of very smart folks. And it seems it can all be traced back to this seminal article written by Hal Chamberlain for Byte magazine in September of '77. I have a link in the description to this issue. And on page 62 is where Hal Chamberlain's article begins. And this is really where a lot of the algorithms for doing computer music originated. So if you want to learn more about how music was done in the olden days and the hardware and software and interesting algorithms, this is the original place to go. And everything I'm doing is based on stuff that people did that's based on stuff that people did that's based on this article. Rather than using this oscillator, which is like a fraction of a single byte of the waveform to play, we're instead still going to use a 16-bit value. But this is going to be capable of skipping around the waveform. So we might start here, and then depending on how quickly we have to cycle through, we might skip over a few bytes and then do this one, and then skip over a few bytes and then do this one. Or if it's a lower frequency note, maybe we're actually playing every one. In fact, maybe we're playing some of these twice still, depending on how low that pitch is. So this value is going to take care of that. This is really two values in one. The high order byte tells us which byte of the waveform to play. So this cycles obviously from 0 through 255, and it represents which of these bytes we're going to play. Byte 0, byte 1, byte 2, or byte 255. The low order byte is a fraction, just like the old oscillator was, but this is just a 1 byte long fraction. So this is going to keep on cycling up, 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 up. Once it hits FF, the natural addition will increment the most significant byte, and that will cause our pointer into the waveform to advance. The frequency value is just as before, so this is just going to be how much we increment this value by. So high frequency notes will have a larger value here, and we'll have us cycling through the waveform faster. Low frequency notes will have a smaller value here, and we'll have us advancing slower through the waveform. So here's our wave pointer in action. It starts off at 0, and this is the frequency value that we're using for the very first note. You'll see it has bits both in the most and least significant byte. So it's actually going to advance the wave pointer by 1 every time, and it's going to advance the fractional part by hex 11 every time. So let's watch and see how this statement will affect the choosing of the next waveform byte to play. The most significant byte of this is simply the A register, and we're using that to index into the waveform table. So if I set a breakpoint here, I can see what happens to A. A is 1, and you'll see that this advanced by the frequency 111. Next time through, this advanced by the frequency again, now it's 222, and A is now looking at 2. And if we keep on going, we'll see at some point this will actually skip a byte because that fractional part is going to catch up with us. But A goes up to 3, and then 4, and then 5, and then 6, And now next time through, rather than A going up to 10, it goes up to 11. This is an example of using a fixed point number instead of a floating point number, which is probably more well known. With a fixed point number, you have a fractional part that's always exactly the same number of digits of precision, and a non-fractional portion that's always the same number of digits of precision. The decimal point doesn't float around. The decimal point stays firmly between the most and least significant bytes of that number. Since we're changing the size of the waveform, we're going to have to change our math a bit when we calculate the special frequency values for each musical note that we want to be able to play. So this was our file, which encoded for each musical note what that special value would be. We spent a while deriving this formula last time, so just as a quick review, if, say, the note that we're trying to encode is the A above middle C, which is 440 hertz, we've got 440 cycles per second for the note, and there are 8 bytes in that waveform, so that's that many bytes we need to cycle through per second. And the interrupt handler is happening 7,860 times per second. So we divide this product by this amount, and we know how many bytes we need to run through each time the interrupt is called. Now that's really just going to be a fraction. It's not going to be more than 1 most of the time. So we scale it up to 65,536. We would have a fraction whose denominator would be 65,536. And this is the number that we add to the oscillator every time the interrupt runs to bring it closer and closer and closer to 65,536, so that when it finally overflows, then we know it's time to move on to the next byte of the waveform. So how do we adjust this now that our waveform is 256 bytes long, and we're no longer doing a fraction over 65,536? In fact, it's not a fraction at all. We just do this. So we take the hertz value for the musical note that we're trying to encode, we multiply it by 256 since that's the number of bytes in the waveform, and then we divide that by 7860, which is the number of times the interrupt handler is called per second. This tells you the number of bytes to advance each time the handler is called. And so what we do is we take the integer portion of this fraction, and that becomes the most significant byte, and then the fractional portion of this value becomes the least significant byte. And then that gives us a list like this. So with a very low note like C0, we don't advance a full byte through the waveform each time. We advance hex 88 over hex FF fraction of a byte, which means this will just keep adding to that wavetable pointer each time, and eventually it'll go up to 1 in the most significant byte, and then we know it's time to read that next byte of the waveform. And the further up the scale we go, the bigger those numbers get, until we find ourselves skipping many bytes each time. So for example, with F#3, each time we're skipping 6 bytes of the waveform, plus an extra 7/256ths of a byte. And if we keep on going up and up and up and up, at some point, the numbers just get too high. So I'm stopping it here at A#8, because if we go beyond that, we actually have to skip the entire waveform. In fact, this already is really pushing it. We're skipping almost the entire waveform, almost all the bytes, to figure out where to go next. So the very highest pitched notes aren't going to sound great, but a lot of them should sound very good and a lot smoother, we hope, than when we just had a measly 8 bytes per waveform. Now that brings me to a big juicy bug. Maybe you noticed it already. Maybe you have an idea what I did wrong, but here's the big juicy bug. Before I got everything working, I didn't want to make 2 different wavetables, so I just reused wavetable sine here for both the sine wave and the square wave. That's not the bug, that's just me being a procrastinator and wanting to make sure things are reasonable before I put in any more effort. That means when the basic driver runs, it's going to play the song with waveform 0, it's going to play the song with waveform 1, and rather than it being played with the square wave first and a sine wave second, they're both sine waves, so it's just going to play it with 2 sine waves. So we would expect to hear the exact same sound being played both times. But the crazy thing is, it's almost like the CoCo knows what I eventually want to do, because the first song is actually going to sound like a square wave, even though it is a sine wave. I should mention that the basic driver code here actually will try to play a third waveform. I don't have a third waveform in here yet. I left the code in anyway because it doesn't really hurt anything. And what's odd is it will actually play those notes a third time using total garbage, using whatever garbage memory is there as the third waveform. And you would expect it to sound completely atrocious, but it actually is pitched. So I just find it interesting that you can play pitched garbage and you can kind of make out the tune. Anyway, so when you hear it play for the third time, that's not the issue. The issue is that the first time sounds like a square wave. So the first thing I did when I noticed this is I went to the list file. This is generated by LWASM when doing the assembly. And I confirmed under the wavetable square label, we're actually including wavetable sine 256. It's starting right at the page boundary at 4600. And dude, that's a sine wave. There's no way that's a square wave. And if I advance further down and compare this with the second time it gets included, it's the same bytes. And then I used MAME after setting a breakpoint inside the interrupt handler. And I asked MAME to show me, okay, starting at 4600, is that a sine wave? And I compared the stuff from 4600 and on and 4700 and on. And if you look in the ASCII portion, it's kind of easier to tell starting from here compared with starting from here and moving on down. They do look the same. And if you look at the numbers, 80, 84, 84, 88, 80, 84, 84, 88. And if you keep on looking, they are the same. They are the same. Now it's the first waveform that seems to be impersonating a square wave. I actually set a breakpoint at the point where we fish the byte out of the supposed square wave to see what the values of the bytes are. So if I set a breakpoint here and continue on, we see we've got an 84, and that's our 84. You'll see that we skip the very first byte the first time through. That's normal. And if we continue on, we get another 84, an 88, an 8C, a 90, and sure enough, another 84, an 88, an 8C, a 90, and I just kept on doing this, and this certainly looks like a sine wave to me. This is not a square wave. Why the heck is it sounding like a square wave? What is going on? So that experience with the debugger rules pretty much everything out, like the set waveform subroutine. Is it really getting the waveform? I think yes, it's getting the one at 4600. I saw it in the debugger. It's literally getting the bytes out of that first copy of the sine wave. Is PlayNote properly initializing everything? Yes, I saw it's getting the bytes out of the sine wave. I also tried doing this. Do waveform 1 first, then do waveform 0. What does that sound like? So even though those bytes are identical, it noticed when I changed the order, because now it played the real sine wave first, and then it played what should have also been the identical same sine wave second, but instead was the phantom square wave that it knew by reading the tea leaves in the future that I would eventually want to put there. What the heck? Okay, ladies and gentlemen, the culprit is on the screen right now. Do you see the culprit? All I can tell you is I did not arrive at this with a methodical debugging methodology. I just kind of had a flash of oh, is it possible that, oh, is this the oh? And it was the O that I thought of. Can you see the O? Do you see the O now? So my flash of insight kind of came from this. These really are the same values. So if I start at 4600 or I start at 4700, it doesn't matter. It's getting the same values. The difference between this and this is not what's stored there, but what's stored before there and after there. And sure enough, this was going outside the range that I was intending. The reason is I'm using indexed addressing, and indexed addressing is a signed operation. It's treating A as a signed byte. A is no longer taking the values from 0 to 255. It's taking values from negative 128 to 128 or 127 or whatever. So when I had very high values of A, it was actually using negative offsets, and it was going before 4600 into whatever happened to be stored before 4600. Whatever garbage was there was getting mixed into my waveform. I had half of a sine wave and half of garbage. And apparently when you put them together, you fool me into thinking it's a square wave. It wasn't even a square wave. What's the fix? Well, the simplest fix is I just look at what Simon did. I just do whatever he did, because you know that works. And of course, he did the much simpler thing. So I'm doing math here. I'm adding A to X, but look, X isn't even going to have its least significant byte set. X is going to be 4600 or 4700. This is written with self-modifying code. The bottom byte is going to be 0 anyway. So I could just store A directly into that location of memory. I'm not doing signed addition. I'm not doing unsigned addition. I'm just overriding this byte with whatever is at A. And here is the fixed code. I'm going to walk through this a little slower than I did before, just so we can see every line and make sure it all makes sense. So this instruction loads D with the pointer into the wavetable. This is going to get rewritten by self-modifying code. So it looks like an immediate value of 0, but instead it's going to be an immediate value of whatever the next wave pointer is. The most significant byte is the actual offset into the wavetable, and the least significant byte is a fraction of the byte that we're offsetting into. Therefore, A is the offset and B is the fractional part of the offset. The next instruction adds to D whatever the frequency value is of the note that we're trying to play. Once again, this is an immediate value and it is getting overwritten by self-modifying code each time we change the note. So this will stay constant as long as we're playing a certain note, while it keeps adding to this over and over again. And that adding happens here. We've updated D with the new wave pointer, and then we store it back. This is the self-modifying code that modifies this. And here finally is the fix. Since the D register is just the A and the B registers, A being most and B being least significant bytes, the most significant byte is A, and we stick A at load wave table plus 2. This is load wave table. This is plus 0, plus 1, and plus 2. These two digits are the digits that are getting overwritten. So this story instruction here overwrites this part. This part over here is just the page. So if the wave table starts at 4600, this will be 46. If it starts at 4700, this will be 47. And then this, rather than adding A to that whole value, I'm just overwriting the least significant byte of that value with whatever is in A with that line there. And then finally, I've loaded A with the value at that location. So A is now the byte that's plucked out of the waveform, and I store it into the DAC. Finally, I acknowledge the horizontal sync interrupt, and I return. And this is my entire IRQ handler. All right, let's take a listen. Now we expect to hear 2 sine waves in a row. So it's worth noting that you don't have to use self-modifying code to fix this. It happens to be more efficient, and we are being hypersensitive to efficiency since this is in the horizontal sync interrupt handler. But another way to go is to make use of this odd little instruction ABX. So if what I did is I transferred the value of A into the B register, then I added the value of B to X, now I can load A with wherever X is pointing now, and that will achieve the same effect that I was trying to achieve. The nice thing about this is it does an unsigned add. So if you ever want to do unsigned indexed addressing, this is a way to go about it. You can add an unsigned byte that's living in B to X, and now X is pointing where you want it to go. What I find so odd about this is there are no other variants of this instruction. You can't add B to Y, you can't add A to X, you can't add A to Y. It's just this. So if you ever want to take advantage of this trick, you're going to want to make sure that you're using the B and the X registers. Well, that covers today's installment of how to improve sound quality, and also of my general incompetence. Next time, we will finally talk about chords. Yes, I've been saying it and I mean it. We're doing chords next time. Thanks for watching.